Welcome, ladies and gentlemen, to our very last lecture of the semester. This lecture is material that you're not going to be tested on. It's just a lecture to briefly and in a very conceptual way cover some material that I think a lot of introductory students are usually curious about, and that's relativity. Okay? I thought it would be nice to just do a lecture with some untested material just for fun, just to kind of sit back and give you some material that's for your culture, as one of my professors used to say. Okay? So, in the early 20th century, Albert Einstein introduced the world to the idea of relativity. Okay? And there are two theories of relativity, both from Einstein. One is called general relativity, and it applies to everything, everywhere, all the time. Okay? And it's the general theory, which means kind of always applicable. And then there's special relativity, which is a special case of relativity for inertial reference frames, okay? Reference frames with constant velocity and flat spacetime. So we're going to start here by first considering special relativity, as it's the simpler case, and we're going to mainly just cover special relativity here. I'll very briefly just mention general relativity, but it's much more complicated and much more difficult to fully explain without the mathematics. Okay, so we're just going to take a very kind of conceptual look at mostly special relativity with just a tiny bit of general relativity. So let's start our discussion by considering moving really, really fast, but with a constant velocity, okay, on some fictitious train. And let's consider two different observers, okay? There's me on the train, and there's you watching me go by on the train, okay? So if you have a coordinate system, and we put, say, the origin right here, you can have some coordinate system that, say, this is the x direction, right? And the origin is on this little point. And then I could also have my own coordinate system on the train, right? And I could have my origin, say, right here, or maybe on me, or wherever. And I could have my x hat in the same direction as your x hat, okay? And the velocity of the train, we'll say, is going this way, and we're going to give it a velocity u, okay? And remember that the Earth is always hurtling around the sun, and it's spinning all the time, right? So when we've been using Newtonian mechanics and assuming that the Earth wasn't moving for all of these problems that we've done, all we're doing is just attaching a coordinate system to the Earth so that it moves as the ground moves, right? Just like in the train, we're going to attach this coordinate system to the train, and the coordinate system moves with the train, okay? So if we did this, and we lined it up so that for you, at your time zero, our origins were aligned, then at any time after that, the point of my origin in your coordinate system is going to be ut, just the velocity times time. Okay, because I'm moving with a constant velocity. And this is just like 1D kinematics, right? So at your t equals 0, my origin was right here, and then I'm moving this way, and so at every time after that, my origin is located at some position u times t. So now, if I'm going by on the train and I throw a ball in the direction of motion of the train with a velocity v, okay, I throw it totally horizontally like this with some velocity v, then I see the ball move away from me with velocity v, right? Again, this is just like when we do our problems where the Earth is moving, but we consider it to be stationary. Our coordinate system's attached to the Earth. If I throw the ball and we only consider what's going on inside the train, I see the ball move away from me with a velocity v. But if you're watching from the side, the ball relative to you, you're going to see it move with a velocity. So this is v from the out. I don't want to use naught because we always use naught for time 0, right? So let's say v for u. So v for u is going to be the velocity of the ball that I throw, but plus the velocity that my whole coordinate system is moving, right? U. So the velocity of the train. And this makes some intuitive sense to us, right? If the train's going by at 50 miles an hour and I throw the ball in front of me at 20 miles an hour, when we go by, you're going to see the ball moving at 70 miles an hour, right? Because it's moving, even if I was just holding it in my hand, it would be moving with the speed of the train, 50 miles an hour. And when I throw it in front of me, it moves that extra amount of speed, right? So 20 miles an hour, so I get a 70 miles an hour total, okay? So these coordinate systems, the one attached to the train and the one that's with you, fixed, they're called frames of reference. And because they have no accelerations involved, they're called inertial frames of reference, okay? So we each have an inertial frame of reference. We each have a coordinate system attached to some constant velocity, okay? In our setup here, we've considered your velocity to be 0, okay? And mine to be u, some velocity relative to u, okay? But now, instead of throwing a ball, let's say that I turned on a light, and we were instead going to look at how fast the kind of front of this light goes, right? Light has a finite speed, so it takes time for it to travel this distance and hit this wall, right? And so we want to know what's the velocity here of the light, okay? So I'll turn it on, and let's say that it's a vacuum for whatever reason. It's a vacuum in the train, okay? And I'll see the light move away from me at the speed of light in a vacuum, c, okay? And this is 2.99792, I think, times 10 to the 8. I think that's right. Meters per second, okay? That's c. It's very, very fast. But so I'll see the light move away from me with speed c. And then what will you see? When you look at the train from the side, you'll see the light moving at a speed c, okay? You will not see the light moving at a speed u plus c, okay? You won't see that. You'll see it moving at c also. And this is really counterintuitive, right? But it's actually a well-tested physical fact. And it's a key concept for understanding relativity. The speed of light in a vacuum is the same regardless of reference frame, okay? So you're going to see this speed the same that I'm going to see it. And that creates some real problems, right? How can I be moving with this speed u, and that doesn't affect the speed that you see for light like it does with the ball? So it doesn't fit with Newtonian mechanics, and Newtonian mechanics tend to be the way that our intuition takes in the world. And so when we measure this, and we notice that this is indeed true, you see it at c and I see it at c, that shows us that there's a problem with Newtonian mechanics, right? It's failing to describe the physical world in this case. And relativity is the answer to this problem, okay? And it follows from two things, just two basic things. First, that the laws of physics have to be the same in all inertial reference frames, okay? And second, that the speed of light in a vacuum is the same in all inertial reference frames, okay? So, based on those two things, we end up with relativity. And that's all well and good. We both measure the same speed of light. So what is the big deal with that? What's the big problem there? Who cares? We just remember that the speed of light's the same everywhere, and then we move on, right? We just always put in c for it. Well, no, that's not right, okay? There are some serious implications to this fact. And as it turns out, the world doesn't work the way that Newtonian mechanics says it does, okay? Phenomena are actually correctly described using relativistic mechanics. And it's just that in the right conditions, the conditions that we live most of our lives in, the results of relativistic mechanics can be approximated very closely by Newtonian mechanics, okay? And I'll show you a little later what I mean by very closely. It is very closely, okay? But the truth is, the actual kind of rules that nature's operating by are described by relativistic mechanics, not by Newtonian mechanics, okay? So, it isn't necessarily that Newton was wrong, but it's that Newton's theory isn't complete, okay? It's correct in our everyday world. We just know now that we've kind of discovered relativity, that it's actually an approximation of a more complicated set of rules that are governing everything, okay? So I said there are serious implications. So what are these serious implications? Well, what am I actually talking about here? Let's go back to our train, and let me see if I can show you one of the serious implications here, okay? So I'm on my train here. I'm standing here, and I have a little thing that's going to emit a pulse of light, okay? And that light is going to travel up to the ceiling. It's going to hit a mirror up here, and it's going to reflect down and be detected again by this little device, okay? So this device emits a pulse that goes up, reflects off a mirror, and comes down, and is detected by the thing. And it goes, for me on the train, straight up and down, some distance d, okay? So if I wanted to measure the time that it took for the light to go up and down, right? I could say that the time interval is equal to 2 times d, that's the distance that it goes, divided by the velocity that it travels. And it's light, so it's going to travel at c, okay? And I'm going to call this t prime for now. You'll see why later, okay? So this thing is just the time that it takes for this whole thing to take place, okay? But now, let's instead consider what you see as you watch me go by, okay? So when the light is emitted, the train is in this position, okay? And then at some time later, when the light gets back to the thing, the train is in some new position because it's moving all the time, right? And this distance that it's covered, remember the train is moving at a velocity with a speed u, okay? Then this distance that's covered is u times t, right? And then at some point, remember this is a constant velocity, so halfway through this process, it reflects off the ceiling. So the path of this pulse of light that you see looks like this, okay? And then if I put a line in here, I'll make a right triangle, okay? And this side of the triangle we can agree is d, right? It has a length of d, just like it did before. And then this bottom side of the triangle must have a length of 1/2 ut, okay? So this L we can find by Pythagorean theorem, right? L equals d squared plus ut over 2, that quantity squared, and that's all in a root. Okay? So then if I wanted to find the time that it took for this pulse to cover this distance, right? The time then is the distance covered, 2 times L, over the speed. And it's light, so it moves at c, right? And it moves at c in every reference frame. Okay? So this looks just like t prime, but I've replaced d with L. Okay? So then, what do I have? I have 2 over c, and then this L is d squared plus ut over 2, quantity squared, in a root. But now, when I look at this time that it took, it's not this time, right? Those are different. D is the same in both cases, and this isn't just D, right? Because this other stuff is in here, okay? So these times are not equal, right? So let's play around with this one a little bit. What if I square this one, okay? Then I would have t squared equals 4 over c squared. And then this square root would just go away when I squared it, right? So that'd be times. Let me distribute. So I'd have one term that was 4d squared over c squared. And then plus, and then I'd have the 4's would cancel, and I'd have u squared over c squared t squared is the other term, okay? So I'm squaring this. The square makes the square root go away, and then I just multiply both of these terms by 4 over c squared, okay? But then if I squared this one, I'd have t prime squared equals 4d squared over c squared. And that's just this first term down here, right? So then t squared equals t prime squared plus u squared over c squared times t squared. And then if I bring this term over to the left, I could factor the t squared out, and I'd have 1 minus u squared over c squared times t squared equals t prime squared, okay? And then that would tell me that t equals t prime over 1 minus u squared over c squared in a root, okay? So what's most notable here? Well, t is not t prime, okay? That is a pretty big consequence of this speed of light being the same everywhere, right? And this t prime is not equal to t. This is not some illusion based on an observer effect, okay? This isn't a trick of the mind or something like that, okay? This is real. The time that's passing in these two places is different, okay? And note that t prime, if I look at this equation here, t prime is always going to be less than t. This is a number that's less than 1, right? So t prime is always less than t. But we agree that the same thing happened, that the light went up to the mirror and then back down again, okay? So when you look in from an outside reference frame, that event took longer to happen than it did for me on the train, okay? The event of the light pulse going up to the mirror and reflecting and coming back down, it took longer to happen in your frame than it did in my frame. And that means that to you, I appear to be in slow motion, okay? And again, this is not a trick in the mind. This is not an optical illusion. This is not an observer effect. This is real, okay? And we call this effect time dilation. This effect where on the moving train I have this clock that's running slow, we call this time dilation. And again, it's real, okay? It's not just that my time appears to be moving at a different speed than yours. My time is actually moving at a different speed than your time, okay? We have taken atomic clocks, which are the most accurate and reliable clocks that we have. We've taken them into orbit to test time dilation, and the clocks do record a different passage of time while they're in orbit, okay? And this time that I've called t prime here, the one where the reference frame was at rest with respect to the event, that is, where the event starts and stops at the same point. So the reference frame where I'm not moving relative to the event that I'm watching, we call that time in the reference frame, in the same reference frame, the proper time, okay? So in this equation that I wrote, it's usually written this way, okay? T equals the proper time times this factor that we usually call gamma, and gamma equals 1 over 1 minus u over c squared in a root, okay? So it's gamma times the proper time. And this means that this is the time in any frame other than the reference frame that produces the proper time. Anyone other than the one where the event is not moving. Okay, so the reference frame that's connected to the event, where the event doesn't move, has proper time. And every other reference frame where that event is moving relative to the observer is going to see this other time. Okay, this one right here. And the u in the equation is always the relative speed between the frame that you're considering and the frame that contains proper time. Okay, so in this case, you were outside, right? And we said that the speed difference between the two was the speed of the train. Okay, so remember, I had my coordinate system connected to the train, right? You had yours connected to the ground. And so my coordinate system was moving with a velocity v, or a velocity u, relative to your coordinate system. Okay, that's how we get the u that goes in here. So we have this time dilation effect, and it's a real effect, but I don't notice it in my reference frame. Okay, in my reference frame, I'm not moving in slow motion. Everything works just like it always does. But everything that's occurring in my reference frame is slowed down to any other inertial reference frame. Okay, so if I'm on some kind of spaceship that's going past you at a speed near the speed of light, I'll be happily chugging along with everything happening at normal speed in my reference frame with my proper time. Okay? And you'll be happily chugging along with everything happening at normal speed in your reference frame with your proper time. But when we look at each other, the relative speed of our reference frames is the speed of my spaceship going past you. Okay? So we'll both say that the other person was moving in slow motion as my spaceship went by. Okay? And this is because I could describe the motion of the ship as either sitting still while everything else moves past it. Okay, so I could say that the ship is sitting still and you're moving past me. Because in an inertial reference frame, there are no accelerations or anything. How do I know that I'm moving? Couldn't it just be that you're moving? Okay? I could describe it that way. I could set up my coordinates so that it's described in that way. Or we could set up the coordinates so that you're sitting still while I go by. Okay? And then when we set up the coordinates that way, it's the ship that's moving. Okay? And both of us are going to feel like we're the ones that should have the fixed coordinate frame. And for proper time, it's going to be the coordinate system that's fixed to us. So your proper time is in the coordinate system that's fixed where you are not moving, okay? And my proper time is the coordinate system that moves along with me, so where I'm not moving. And for each of us, the time that we see for events to occur is going to be this slowed down time based on however fast the two coordinate systems are moving relative to each other. But now let's go back to the train again, and let's consider a little bit different situation. Let's consider the train chugging along. I'm right in the middle of it, okay? And there's a light on either side, okay? And these lights turn on such that for you out here watching the train go by, the light reaches you at the same time from both lights, okay? So for you, the lights turn on simultaneously, okay? And remember, I'm moving in this direction, okay? Now, because I'm moving in that direction, the distance that the light has to travel to get to me from this front one, D1, is shorter than the distance that this back one has to travel to get to me, right? And remember, light moves the same speed in every reference frame. So you're going to say that the lights turned on at the same time, but that I saw them at different times, okay? But in my reference frame, the lights are both equally far from me, and the light travels at the speed c, okay? So the only way that I can possibly see them at different times is if they don't turn on at the same time, right? I have to see the front light turn on first, and then the back light, if the light is going to reach me at different times, because in my reference frame, they're the same distance from me, right? And here's the thing, we're going to agree on this. I am also going to say that the light from both lights reached you at the same time and that it reached me at different times, okay? But in my reference frame, the light had to travel the same distance from both lights to get to me. So in my reference frame, the lights did not turn on at the same time, okay? This is another real effect. It's not some illusion playing tricks on us, okay? The entire notion of this kind of universal simultaneity of events, of two events in different places happening at the same time, it's dependent on reference frame, okay? Actually dependent on reference frame, not just appears to be. In my reference frame, the lights do turn on at different times, okay? And in your reference frame, the lights do turn on at the same time. So when we're dealing with relativistic mechanics, we have to account for the fact that two events being simultaneous is based on the reference frame that we're in, okay? Now, there are many apparent paradoxes from relativity that can occur because we can't release this idea of universal simultaneity, okay? When we remember that simultaneity is dependent on reference frame, many of these paradoxes cease to be paradoxical, okay? So we have time dilation from relativity, and we know that relativity kind of blows up our idea of universal simultaneity. But there's one other big consequence in special relativity that I want to tell you about, okay? And in the interest of time, I'm going to skip kind of a derivation of this one. I'm just going to tell it to you, okay? It's called length contraction, and it's exactly what the name implies, okay? So for some length L in your reference frame, that length is L prime, the length in my reference frame, times the root of 1 minus u over c squared, okay? So in other words, in a given reference frame, objects are going to be shorter than their proper length, okay? Or their length in the reference frame where they're at rest. And again, not a trick of the mind, not an observer effect, a real effect. The things are actually contracted in other reference frames, okay? And in particular, it has to be the direction that's contracted is the direction of my motion, okay? So if I'm moving along with u here, the length that's contracted is the length of the train. So if the train is this wide and I'm moving with speed u, as I go by you, the train might seem this wide. Not seem, actually be this wide with me in the middle, okay? But it's still going to be the same height because in this direction, the train's not moving, right? In that direction, the train is at rest in my reference frame and in your reference frame. So the size of the train in that direction isn't contracted, okay? In this y direction here, it's not contracted, okay? So it's actually going to change the shape of the train because it's going to shrink it only in the direction of my velocity, okay? So these three effects here, time dilation, length contraction, and then this little diagram showing that simultaneity is dependent upon reference frame, those effects kind of complete our little brief conceptual view of special relativity, okay? These are the big consequences that come out of the fact that physics needs to be the same in every inertial reference frame, and that the speed of light is the same in every inertial reference frame, okay? So when things are moving very fast, they have to be going very fast to notice this effect, they experience time dilation, okay? They don't have to be moving very fast to experience time dilation. They have to be moving very fast for us to notice it, okay? Any movement is going to cause time dilation. It's usually just on a scale that's so small that we can safely just ignore it, okay? But anytime something's moving at some constant velocity, it's going to experience time dilation. It's going to experience length contraction. And our idea of universal simultaneity, it goes out the window, okay? And these are all real effects. They're not illusions. They're not just some kind of trick of the observation. They all are true. They're all real things that are happening, okay? And this is mind-bending to think about. In Newtonian mechanics, remember, we had this three-dimensional space, right? And then kind of on the side over here, we had time, right? We have things kind of flying around in space, and we just have this clock ticking away for everything everywhere all the time, right? We just have this kind of separate idea of time. But in relativity, we don't just have this clock sitting on the sidelines, do we? We see that our motion affects the time, okay? The clock is part of the action. He's in on the game now, okay? He's integral to everything, and he interacts with what's going on, okay? The clock is a part of space. What happens in space affects the clock. And so what appears in Newtonian mechanics to be two separate things, space and time, is actually all one interacting thing, okay? All one big thing. And we call this thing space-time. And we call it space-time because physicists are generally not very creative when they name things, okay? We're like, I don't know, it's made up of both space and time, so it's space-time. And this notion, this shift in thought to say that time takes part in the game, that time is affected by what happens in space, this is a monumental shift in the way we think about things. Okay? So then, why does Newtonian mechanics usually work just fine on Earth? Why don't we usually need to consider relativity in our everyday lives? Why could we spend this whole semester where I just teach you Newtonian mechanics and that works totally fine? And then you don't usually even need to have a class specifically on relativity for, say, an engineering degree or something like that, where we just apply physics as our job, right? Why is that the case? So to look at this a little bit, why Newtonian mechanics usually works just fine, let's consider the speed that things are moving at in our everyday life. So let's say that I put you on a train, okay? And that train was going at u equals 1,000 miles per hour, okay? Now, that is almost certainly faster than you have ever moved in your entire life, okay? 1,000 miles an hour. That's equal to 447 meters per second. It's pretty unlikely that you've moved faster than that before. Although I think not impossible. There might be a couple of very particular, like spy planes, spy jets that can fly that fast. Maybe. Or if you've been on the space shuttle, you've been going that fast before, relative to the Earth. The Earth, of course, is moving much faster than that, but you've never moved that fast relative to the Earth, most likely. Okay? And probably not even close. 1,000 miles per hour is probably, an order of magnitude faster than you've ever moved before. Okay? So let's say that some event on the train took exactly 3 seconds. 3.00, zeros out as far as you want to go seconds. Exactly 3 seconds on the train, okay? So the proper time on the train, this event takes 3 seconds. So if I was watching it from the outside, and I watched you do whatever this event was that took 3 seconds from the outside of the train, how long would that event take? Okay, how long would it take in my reference frame going 0 miles per hour? So t is equal to t prime over 1 minus c over, that's upside down, u over c squared in a root, right? And c is this number up here. So if I plug in those numbers, okay, then what I get for the time that I measure on the outside is 3 seconds. Okay? It's actually so close to 3 seconds that my calculator just says 3. Okay? So what I did is I got online and I found a calculator with really fine accuracy, something that would go out way further than what my calculator will go out. Okay? And then if I plug in this what I get for the time that I measure on the outside, remember your proper time was exactly 3 seconds. The time that I get on the outside is 3.00000000003 seconds. Okay? So that's a 3, a decimal point, 11 zeros, and then a 3. Okay? So for all intents and purposes, that's 3 seconds, right? It took 3 seconds for you on the train. It took 3 seconds for me to the side of the train. Okay? And that's at a speed that's probably faster than you've ever moved before. Okay? So the effects of relativity, they do exist. All right? They do exist at kind of the level that we live at. But they're so small that Newtonian mechanics is, while technically an approximation, it's an approximation that's so good that we can just say it's correct. Okay? It's an approximation that's making essentially no error at the kind of the speeds that we live at. Okay? Now, there are things in the world for which we must take relativity into account. Okay? There are particles that radiate us from space that are moving at near the speed of light. Okay, when we consider those particles, we have to consider relativistic effects on them. Okay, there are particles that come in and hit the atmosphere of the Earth at these incredible speeds, and when they hit the molecules in the Earth's atmosphere, they create a whole shower of particles. And these particles go down to the Earth, and they come down to the surface of the Earth. And one of the particles that comes down is called a muon. And a muon has a lifetime, and the lifetime in this sense is the amount of time that it takes for the muon to decay into something else. Okay, for the muon to basically die and become some other particle. Okay, the muon's lifetime is so short that even at the speed it's moving, it wouldn't be able to make it to the surface of the Earth. Okay? But we measure muons on the surface of the Earth all the time. There's a constant shower of them. You can make detectors of these that just tick away and just catch muons coming down from the atmosphere all the time. Okay? And the reason that these muons are always there is because the muon experiences time dilation because it's moving at nearly the speed of light. And that makes its lifetime much, much longer when you look at it in our reference frame. In its reference frame, it still has the same lifetime that it has when it's at rest at any given time. But in our reference frame, that's slowed down so much that the muon actually has a lifetime that's long enough that we detect them on the ground all the time. Okay? And it's due entirely to time dilation that the muon can make it down to the surface of the Earth. So the last conceptual thing that I want to point out with special relativity is that this thing that we're calling the speed of light in a vacuum, c, it doesn't actually have anything to do with light. Okay? The speed of light in a vacuum is actually just the speed limit of the universe. Okay? It's as fast as anything can move through space. Okay? Or through space-time. So this maximum speed that something can move through space-time with is unattainable for most things because the energy needed to reach that speed increases as we go faster. So for anything with mass, it can never reach this speed. But any kind of a massless particle can potentially move at the speed limit of the universe, okay? And light just so happens to be a massless particle, okay? So this speed, the speed of light in a vacuum, it doesn't have anything to do with the properties of light per se. It's just the speed limit of the universe, and a massless particle, like a photon, gets to move at that speed limit, okay? As long as it's not interfered with by anything else. Light actually does slow down when it moves through other media, like water, air, things like that. But in a vacuum, a massless particle like a photon can move all the way up at the speed limit of the universe, okay? And so we call it the speed of light in a vacuum because that's how we first noticed it, that's how we first measured it. But in fact, c is the speed limit of the universe, and any massless thing can move at speeds of up to c. And light just happens to be one of those massless things. So now finally I'm going to end by very briefly mentioning general relativity, okay? The mathematics involved in calculating quantities in general relativity are much more complicated than in special relativity, okay? And we just don't have the tools right now to do this. But I can tell you a little bit about it just conceptually, okay? So general relativity takes the same basic concepts as special relativity, but it allows us to apply them to non-inertial reference frames. In particular, general relativity tells us how gravity works. So general relativity tells us that gravity comes from a curvature of space-time. And I have this picture here that I got from the ESA, the European Space Agency, from their website. Because, boy, this is one instance where we really don't want to rely on my drawing ability. Okay? And this is just kind of a conceptual thing. You can imagine space-time, of course, is three-dimensional. But if we simplify it to be two-dimensional, this gives us an idea of what's going on here. Okay? We have massive objects. We have these different balls of different masses. And they're in this case, two-dimensional space-time. And they cause this curvature. Okay? They cause this kind of dent in space-time. Okay? And then when these massive objects curve space-time, when something flies through space-time, it flies along a line that has a shortest path, okay? So when space-time is flat, the shortest path between 2 points is a straight line. When space-time is curved, then the shortest path between 2 points becomes a curved line. And so what happens is this thing will come in and curve like this as it flies through curved space, okay? And then when it gets back to flat space, it goes straight again, okay? And anything works this way. Anything traveling through space-time will work this way. And they follow these curved paths of shortest distance. So objects always move through space by moving at whatever the shortest distance between 2 points is. But that shortest distance is modified when space-time is curved, okay? And in a curved space-time, the shortest distance between 2 points actually becomes a curve, okay? And this theory explains how gravity actually works. Remember that when we had Newtonian gravity, we just said that it looked like this, right? And this just described the way that things act, right? That these two objects, big M and little m, that they'd be attracted to each other. It doesn't tell us why those two objects are attracted to each other, only that they are, right? In general relativity, we have this curved space-time, and that tells us why the two objects move toward each other, because it changes the shortest path, okay? So their motion, this curve, the shortest path is modified such that the two objects appear to be attracted to each other, okay? This tells us how gravity works. Gravity is the distortion, the curvature of space-time. And this curved space-time also causes time dilation, and it causes length distortions, and it blows up our idea of universal simultaneity, okay? Just like special relativity did. And in fact, for GPS satellites to work correctly, they have to account for time dilation that occurs relative to the surface of the Earth as they orbit, okay? And this effect is actually primarily due to the gravitational effects of being at higher altitude in Earth's gravity, okay? The time dilation that these GPS satellites experience is mostly because they're shallower in this gravitational well, right? We're way down here on the surface, and they're up here shallower in the gravitational well, okay? The time dilation that they experience because of the incredible speed that they're moving at is actually a much smaller effect than this gravitational time dilation effect. Okay? So, general relativity tells us that massive objects curve spacetime, and then everything that moves through space follows curved paths as it travels through this curved spacetime. Okay? And this curved path is what we call gravity. That's what we call the effect of gravity. And special relativity, the thing that we looked at in the beginning, it considers inertial reference frames, which are the special case where space-time is flat. So in my picture, it's kind of this area over here, right, where everything is just flat. That's what special relativity considers, okay? General relativity can consider places where spaces are flat, but then can also include spaces where space-time is curved like this, okay? So think about our Newtonian gravity again. And remember we have this big M, little m thing going on, right? And this makes a lot of sense when we have something like the sun that's the big M and it curves space-time, and then that causes something like the Earth, the little m, to take a curved path through space-time, right? And the path of shortest distance is this new kind of curved geometry. But then, what if we take the little m and make it 0? Right? What if we had a massless thing? Well, then our Newtonian gravity tells us that the force of gravity on this massless thing is 0, right? But if we look at general relativity, the object moving through this curved spacetime, that didn't have anything to do with the object's mass, did it? I said that anything moving through curved spacetime is going to have its path deflected, right, due to this curvature. And this is a key difference between Newtonian gravity and general relativity. And it's not just a simple key difference. It's one that we can measure, which makes it a really important key difference, right? And so in GR, the sun causes space-time to curve, and anything moving through the space-time follows a curved path through that curved space, okay? And this includes something massless. And what do we know that's massless? Well, light is massless. And so, in general relativity, the path of light should be curved by this curved space-time. And indeed, during a solar eclipse, so if the red ball here is the Earth, the moon gets in the way, right? And we have a shadow. And that makes it so that the sun doesn't blind us when we look up there, right? There were stars that we should not have been able to see because the sun is in the way, but some of their light is curved by general relativity around the sun so that it comes to Earth. So the light is moving straight this way, it gets curved inward like this, and it comes to the Earth like this. And this was actually one of the first experimental confirmations of general relativity. We can indeed, during a solar eclipse, see stars that should be blocked by the sun based on their position, but we can see those stars because their light that would have missed us, that wouldn't have gone to Earth, is curved by the sun's gravity and hits Earth. Okay, so we see these stars. And what they look like, because normally when we look at stars, we just look like this, right? So what they look like in these, they used plates back then on the cameras, and these plates that they took pictures of the solar eclipse with, it looks like these stars are in the wrong spot. And you have to measure very, very carefully because they're very far away. But you can see that certain stars during the solar eclipse are in the wrong spot. And it's because light is also affected by this curved space-time, okay? And in Newtonian gravity, that wouldn't have been the case, right? The light would have been unaffected by the sun because it has no mass. And this was, I believe, the first experimental evidence that confirmed general relativity, okay? And it came, I think, a few years after Einstein's paper on general relativity. But since it was introduced in these many, about 100 years or so since then, it's been one of the most extensively tested scientific theories ever. And every single time, the results come out exactly as relativity says they should. Not about right. Exactly like general relativity says they should come out. And at this point, we can consider relativity a scientific fact of the universe. So that's where I'm going to stop this lecture. This was our final lecture of the semester. I hope that this semester went well for you, and I hope that this class has given you things that spurred your curiosity and led you to think more about why things work the way that they do.